Um, there is this specific graph in the AI research world right now that is, frankly, it's starting to look less like a curve and more like a vertical wall.
Yeah, a very intimidating wall.
Right. And it's not a graph of performance or, capability. It's a graph of cost.
The literal financial cost of training these massive models.
Exactly. We are looking at training costs tripling roughly every year. We are talking hundreds of millions of dollars to train a single model.
Mm.
And that financial reality, it's forcing a lot of people to ask a very uncomfortable question. Are we doing this entirely wrong?
It is the elephant in the room for the whole industry because pretty much everyone has bet the farm on one specific way of doing things, autoregressive modeling.
Right.
And the assumption has basically been, well, if we just make it bigger, if we throw more GPUs at it, it will eventually get smarter.
But today we're looking at a stack of papers that actually challenges that exact assumption. We are doing a deep dive into a completely new architecture. It's called LLaDA, which stands for Large Language Diffusion with Masking. And the core premise here is just wild.
It really is.
It suggests that the best way to build artificial intelligence might not be guessing the next word at all.
Right. It suggests that the whole next word paradigm might actually be a trap, or at the very least, a local maximum that we are just about to hit the absolute ceiling of.
Okay, so to get into this, we have a couple of sources. We've got a paper by Du and Kelbling that really highlights the problem with these gigantic monolithic models and those exponential costs we just talked about. And then the main event, the paper by Ni, Zhu, and their team introducing LLaDA. Our mission today is to unpack how LLaDA works, why it breaks this thing called the reversal curse, and whether next token prediction is actually necessary for AI intelligence.
And to really understand the solution, we do have to nail down the problem first. You mentioned autoregressive modeling.
Right, the engine under the hood of basically everything. ChatGPT, Claude, Gemini, LaME.
Almost all of the big names use it, yeah.
So for anyone listening who isn't deep into the engineering side, what exactly makes those models autoregressive?
Okay, so imagine you are a bricklayer building a wall, but you have a very, very strict rule. You can only lay one brick at a time, and you must lay them strictly from left to right.
Okay.
You lay the first brick, then you look at that brick and decide what the second one should be. Then you look at those two and decide on the third.
And I'm guessing you can never go back.
Never. You cannot look at the whole wall and say, oh, actually, that first brick is slightly off center. Let me fix that. You are entirely committed.
Wow. Yeah.
In mathematical terms, this is what the paper refers to as equation 2. It basically defines the probability of a sentence as the product of the probabilities of each word, given only the words that came before it.
So it's a rigid chain.
It's a chain.
Oh.
And to be fair, this has worked incredibly well. It's why GPT-4 is so good at writing essays, just follows the chain beautifully. But this left-to-right bias, it creates some really bizarre cognitive blind spots.
Which brings us perfectly to the reversal curse.
Ah.
I read about this in the LLaDA paper, and honestly, I had to read it twice to actually believe it.
Yeah, it's one of those things that seems impossible until you really understand the architecture behind it.
So the paper gives this example about poetry. If you give a state-of-the-art model like GPT-4o, the smartest thing we have right now, a line from a famous poem, and you ask it to complete the next line, it does it perfectly.
Right, because that's forward prediction. That is exactly how it was trained to behave.
But if you give it a line and ask for the previous line,
it completely fails.
It doesn't just struggle, it totally collapses. The paper cites a drop in accuracy from over 82% going forward all the way down to about 34% going backward.
And think about what that implies for a second. It implies the model doesn't actually know the poem as a holistic concept or a structure.
Yeah.
It only knows the sequence.
Right.
It's like if I asked you to recite the alphabet, easy, right? A, B, C, D.
Sure, I can do that.
Now recite it backwards, starting from Z at the exact same speed.
Oh, man. Z, Y, X, W. Yeah, I have to stop and really think about it.
Exactly, because you have to simulate the forward sequence in your head to find the previous letter. That is the fundamental limitation of autoregressive models. They are monolithic in their directionality. They can't see the whole picture, they only see the timeline.
And this is exactly where LLaDA steps in. It proposes a completely different way of generating text. It uses diffusion. Now, I know diffusion, but mostly from image generators. Like, I type cat eating pizza into Midjourney, and it gives me a picture.
Right. And the way Midjourney does that is by starting with static, just pure noise, and it slowly refines that noise into an image.
But here is where I got totally stuffed reading the paper. Images are made of pixels. Pixels are continuous. You could have a pixel that is 50% gray. You can fade from one color to another very smoothly.
Exactly, yes. That is continuous diffusion.
But words are discrete. You can't have a word that is 50% cat and 50% dog. It's either one or the other. So how in the world do you diffuse text?
And this right here is the primary technical breakthrough of the LLaDA paper. They realized you cannot use fading noise like you do with images, so instead they use masking as the noise.
Masking, like redaction in a classified document.
Precisely. Imagine a clean sentence. To add noise to it, you just randomly replace words with a mask token. If you fully destroy the sentence, if you take it all the way to pure noise, you just have a long string of mask, mask, mask.
Okay, so that's the blank canvas.
That's the starting point. The model looks at this string of empty masks, and instead of writing word 1 and then word 2, it looks at the entire sequence simultaneously. It tries to predict all the mask tokens at once.
So it's definitely not a bricklayer anymore. It's, well, what's a better analogy here?
It's a sculptor. A sculptor doesn't build a statue from the toes up, finishing the feet completely before even looking at the knees.
Right, they start with a block.
They look at the whole block of marble. They chip away at the head, the arm, and the leg all at the same time. They refine the overall shape first, and then they get into the fine details.
So mathematically, this is what the paper calls equation 1. It focuses on optimizing the joint distribution of the whole sequence, rather than just the conditional probability of the next step.
Yes, that's exactly it. LLaDA might figure out the subject of the sentence and the punctuation at the very end, long before it figures out the adjectives in the middle.
That is fascinating, and it captures the global context first, which leads to, honestly, what I think is the coolest part of the mechanism. They call it semi-autoregressive remasking.
It really is an elegant solution.
Walk us through a generation step. How did that actually happen?
Okay, so the model starts with all those masks we talked about. It takes a guess at filling every single one of them in all at once. Let's say it generates a draft sentence.
Is the draft any good?
Probably not at first. It's just the first pass. Some words will be high confidence. The model is thinking, I'm 99% sure this word is the, but other words will be low confidence, just gibberish or completely wrong context.
So what does it do with the gibberish?
It keeps the high confidence words, the parts it's really sure about. And then, and this is the key, it remasks the low confidence words. It essentially deletes them.
It deletes its own bad word.
Right. It says, okay, I know the sentence starts with the and ends with galaxy. Now, given the solid anchors, let me try to fill in the middle section again.
It's highly iterative. It's honestly like me writing an email. I blast out a terrible draft. I read it over. I say that middle part makes no sense. I delete it, and I rewrite it based on the good parts that I kept.
Exactly like that. And it does this over roughly 64 steps. It refines the whole thought bidirectionally until the sentence settles into a coherent final state.
That sounds absolutely fantastic in theory, but usually when we hear about these alternative AI architectures, there's always a catch. And usually the catch is that it doesn't scale. Like, you can build a cool toy model, but if you try to make it big, it just breaks.
Yeah, and that was the heavy skepticism going into this. But Nianzhu didn't build a toy model here. They train LLaDA on 2.3 trillion tokens.
Wow, that's a serious number.
That is fully industrial scale. They used about 130,000 GPU hours on H800s. They scaled the model up to 8 billion parameters. They essentially wanted to prove, beyond a shadow of a doubt, that this architecture can stand toe-to-toe with Llama and GPT.
And does it? Because the paper has a ton of charts, and specifically I'm looking at figure 3, which compares the scaling laws.
The short answer is yes, it absolutely scales. Figure 3 shows that as they added more compute, more FLOPs, LLaDA got smarter at the exact same rate as the autoaggressive baselines.
That is a massive validation for them.
It is. It proves that diffusion is a viable path for high-performance AI, not just some niche laboratory experiment.
Okay, so it scales. But does it win? If I pit LLaDA 8B against LMI3 8B, who actually takes the belt?
It's a bit of a split decision, but the nuance is what really matters here. If you look at tables 1 and 2, LLaDA is competitive across the board, but it actually wins in some very specific telling categories. For instance, it outperforms LMI3 on GSM-8K.
That's the grade school math benchmark, right?
Yeah, right. Now ask yourself, why would a diffusion model be better at math than a next word predictor?
Well, thinking back to the whole bricklayer analogy, if you're doing a complex math problem, you usually need a plan. You need to know where the equation is going.
Exactly. Autoregressive models are notoriously terrible at planning because they simply cannot see the end of the sentence. They just spit out a number and hope the next word leads them to the right conclusion.
Whereas LLaDA sees the whole picture.
Yes. It can structure the logical steps of a math problem much more effectively because it's optimizing the joint distribution of the entire solution at once, not just guessing the next digit.
It also did really well on simple instruction following. I think there's this misconception that diffusion just generates static, weird things. But they fine-tuned this model to actually chat, didn't they?
They did. They used supervised fine-tuning, or SFT, on about 4.5 million instruction pairs. The paper actually shows examples of multi-turn dialogue, like chatting about the pros and cons of cats versus dogs, and then pivoting to ask about specific pet care.
So it feels normal.
Totally normal. It holds the context and flows just as well as a standard chatbot you'd use today.
But I want to go back to the reversal curse, because this is the craziest part. We established earlier that GPT-4o, the heavyweight champion of the world, can't recite a poem backward to save its life. 34% accuracy. How did LLaDA do on that exact same test?
This is genuinely the mic drop moment of the paper for me. They ran the exact same poem completion task in section 3.3. LLaDA's forward accuracy was decent. It was about 51%, lower than GPT-4, obviously, which makes sense given it's an 8 billion parameter model compared to a massive trillion-plus parameter model.
Sure, it's a much smaller brain.
But the backward accuracy, it was 45.6%.
So barely a jock at all.
The gap is totally negligible. And if you look purely at the backward score, this tiny 8 billion parameter model handily beat GPT-4o.
That is just wild. A tiny model beating the smartest AI in the world simply because it doesn't have a rigid direction.
To LLaDA, time is basically a flat circle. The beginning of the sentence and the end of the sentence are just two data points in the exact same field. It doesn't privilege the past over the future.
This seems to have huge implications for how we even think about intelligence. Because we've spent the last 5 years basically equating intelligence with predicting the next word. But this suggests that features like in-context learning, where the model learns from the prompt you just gave it, aren't just magic tricks specific to next word prediction.
Correct. The paper strongly suggests that in-context learning is a property of generative modeling in general. If you build a statistically good model, whether it's a bricklayer or a sculptor, that intelligence emerges naturally. It decouples reasoning entirely from directionality.
I want to talk about speed for a second, because one of the biggest complaints about diffusion in images is that it's incredibly slow. You have to wait for the steps to render. Is LLaDA slow?
It depends on how you configure it, but potentially it's actually much faster.
How can it be faster if it has to do 64 steps of drafting and refining and deleting?
Because it does the whole sentence at once. Think about an autoregressive model again. If you want a 500-word answer, it has to run a full pass of the model 500 separate times, once for every single word. It's strictly serial processing.
Right, wait for word 1 to get word 2.
Exactly. LLaDA might run the model 64 times for its steps, but in each of those steps, it's refining all 500 words in parallel.
Oh, I see. So the overall throughput is higher.
Yeah, they highlight this in Figure 5. With fewer sampling steps, say cutting it down to 32 steps, LLaDA can actually be 1.5 to 1.8 times faster than LMA3 for long generations, and that's without even using common optimization tricks like KV caching that standard models rely heavily on.
So it's faster for long text, it scales smoothly, and it can think in reverse. Why aren't we all using this tomorrow? What are the actual limitations right now?
Well, there are a few friction points. First off, it's still very raw. It hasn't gone through reinforcement learning from human feedback, or RLHF.
So no safety guardrails or alignment yet.
Not really. It hasn't been aligned to be perfectly polite or helpful in this specific sanitized way ChatGPT has been. It's strictly a base model right now.
And there was a technical quirk about generation length too, right?
Yes, this is a very distinct difference in how you use it. With a standard LLM, you ask a question, and it talks until it decides it's done. It generates a stop token. With LLaDA, currently, you sort of have to define the canvas size first.
You have to write me exactly a 100-word answer.
Roughly, yes. You have to set the sequence length as a fixed hyperparameter. Now, the authors do note that the model is pretty robust. If you give it 128 slots and it only needs 50 words to answer, it just pads the rest gracefully. But it's not as seamless as the open-ended generation we are all used to.
Is it a deal breaker for the architecture, though?
I don't think so at all. It feels like a software engineering problem, not a physics problem. They can easily build dynamic sizing wrappers around the core model.
So if we zoom out and look at the big picture here, we have the Dew and Kalbling paper telling us that the current monolithic models are becoming way too expensive and too rigid. And then we have the No and Zhu paper offering this sculpting alternative that actually solves the foundational reasoning flaws of the current giants.
It really feels like a major pivot point. For the last few years, the entire research community has been hyper-focused on optimization. How do we make the transformer slightly better? How do we make the data set slightly cleaner? LLaDA is this massive reminder that we can still fundamentally change the architecture itself.
We don't have to just optimize the bricklaying. We can switch to marble.
Exactly. And think about what this means for things like chain of thought reasoning. Right now, when we ask an AI to think step by step, it's still just guessing the next word of its own thought process. It can easily hallucinate a bad step, and then it's completely stuck following that bad logic because it can't go back and fix it.
Because it's autoregressive. It committed to the bad step in the chain.
Right. But a diffusion model, it could draft a whole chain of thought, realize that step 3 leads to a logical contradiction in step 5, and then rewrite step 3 before it ever shows you the final answer.
That is the thoughtful architect versus the fluent babbler.
That's the absolute dream. Moving from models that just sound really smart to models that can actually plan a coherent path through a complex problem.
It really challenges the whole idea that language is strictly linear. Sure, when we speak one word after another, but we don't think one word after another.
We definitely don't. Our thoughts are diffused. They are these abstract clouds of meaning that eventually crystallize into linear sentences. LLaDA mimics that underlying cognitive process much more closely than a ticker tape machine does.
It's truly fascinating. The paper is definitely heavy on the math, but the philosophy behind it is incredibly intuitive once you grasp the analogies.
It really is. It's a proof of existence above all else. It shows the whole industry that the next token dogma isn't some unbreakable law of physics. It was just the first method that worked well at scale.
And now we officially have a second method.
And competition usually drives the most exciting evolution.
Well, I want to leave everyone listening with a final thought based on what you just said. If LLaDA can reason backward as easily as it reasons forward, simply because it sees the whole picture at once, what other cognitive barriers might completely fall apart if we stop forcing AI to think in a straight line?
That really is the billion-dollar question. If we stop forcing AI to strictly talk, maybe we can finally teach it to actually think.
A completely fascinating possibility. And that wraps up this deep dive into LLaDA and the emerging world of language diffusion. We highly encourage you to check out the sources if you want to dig into the charts and see the remasking math for yourself.
It's definitely worth a closer look.
Thanks for joining us on this deep dive, and we'll catch you on the next one.